artificial intelligence. I mean, it's no longer this futuristic concept, is it? It's here. It's approving our mortgages. It's guiding medical decisions. And yeah, it's probably shortlisting candidates for your next job. The scale of it all is just incredible. But it brings up this one huge question. Can we actually trust these systems to be fair?
Yeah, the question, isn't it?
Yeah.
That's the real ethical knot we're trying to untangle in AI right now.
Hmm.
We have this tendency to think algorithms are objective just because, they're based on math.
Yeah.
But the data they eat,
What?
it's anything but neutral. It's full of our history, our choices, all of our societal baggage.
And that is exactly our mission for this deep dive. If you, listening right now, want a real shortcut to understanding ethical tech, then this is for you. We're giving you a blueprint for what's called responsible AI. We're going to get specific, looking at how to detect and correct bias with actual concrete metrics. You'll walk away from this understanding exactly where those shiny accuracy scores fail and how we find the real story.
Yeah. And responsible AI, I mean, at its core, it's just a framework for balancing all that cool innovation with, well, with integrity. When you delegate these huge decisions like who gets a loan or who gets a life-saving treatment, you have to demand that the algorithms meet some kind of ethical standard.
Right. And we know that framework has 5 big pillars: transparency, accountability, privacy, safety, and of course, fairness. Today, we are really going to get into fairness because it's probably the trickiest one. Before you can fix the bias, you have to understand how it sneaks into the code in the first place.
The first thing to internalize, I think, is that the AI model itself, it doesn't invent bias. It doesn't have any malice. It's just a mirror. It perfectly reflects the unfairness that's already out there in the world in the data we give it.
So it sounds like bias isn't just one single point of failure. It has multiple ways in.
Oh, absolutely not. It's insidious. There are at least 6 different ways it can systematically creep into an AI system. And what's really critical is that most of it is unintentional. People aren't sitting there trying to build a biased model. They're just training it on the world as it is.
Okay, let's walk through those 6 sources. I imagine the most common one has to be the data itself.
Exactly. That's data bias. Just imagine training a hiring model on, say, 50 years of data from an industry that was historically, like, 90% male. The model, just being logical, learns that being male is a very strong predictor of getting hired. The data just doesn't represent everyone equally, so the model learns an unequal past.
So it's just
Okay.
statistical proof of old inequalities.
Yeah.
Okay, so what's the next entry point?
That would be algorithmic bias.
Hmm.
This is a bit more subtle. It's where the math itself, or the choices the engineer makes, unintentionally gives too much weight to certain features. So if an algorithm is just told to be as accurate as possible, with no other rules, it might find these shortcuts that happen to rely on biased demographics.
I can see that happening, but what if the data is just labeled wrong to begin with?
That's label bias, and it's a huge one. This is when a human's subjective opinion gets baked into the data and treated like a fact. So, for example, if hiring managers consistently label candidates from, say, certain prestigious universities as excellent, the model learns that subjective preference as if it were objective truth. The AI is basically learning human prejudice that's been disguised as data.
So the model starts to distrust anyone who doesn't fit the profile of the people who created the labels. Wow. Okay, that's 3. What about moving a model to a new place?
That's contextual bias. You build a model that works perfectly in one environment, say detecting credit card fraud in the United States, then you try to use that same model in, I don't know, Southeast Asia, where financial habits are totally different. It's going to fail. It's applying assumptions that just don't belong there.
That makes total sense. And the last 2?
Tool bias. This one is really sneaky. It's about subtle assumptions built into the open source tools or libraries that we all use. If those foundational tools weren't tested across all kinds of populations, they can carry their own little systemic flaws.
And the final one.
Implicit bias. This is the really invisible stuff. It's the patterns the model finds from correlations you'd never expect. Like it might link zip code to credit risk, even if you told it to ignore race. It's connecting these invisible dots that reflect hidden societal structures.
It is so clear we can't just trust the data. We need specific tools to test for all this hidden ethical debt. Let's get into the practical example you brought because it really shows how raw performance numbers can be so misleading.
Absolutely. We looked at a super common scenario, a simple hiring data set. We used a candidate's years of experience and their gender to try and predict if they were shortlisted for a job. And we set up a comparison, a little test between 2 different models.
Okay, so tell us about these 2 models. What data did they get to see?
So Model A got everything. It could use both the candidate's gender and their experience. Model B, on the other hand, was intentionally restricted. We only let it use experience. We explicitly hid gender from it.
And this right here is where so many people, even some data scientists, would just stop. Because Model A, the one with all the data, it produced metrics that looked, absolutely perfect.
It really did. Model A had an overall accuracy of 0.95. It's precision, which means of all the people it said would be shortlisted, how many actually were was a perfect 1.00. We even checked its AUC-ROC score, which is a key performance metric, and that was also a perfect 1.0.
So if I'm the boss, I see that 100% precision score and I say, great, job done, ship it, this is flawless. Why is that so dangerous?
Because those traditional metrics, accuracy, precision, they are completely blind to how the predictions are distributed. They only care about getting the overall outcome right. So if 90% of your historical data was biased against one group, the model gets a really high accuracy score by just perfectly replicating that bias. It's being highly accurate at being unfair.
A system that is technically perfect but ethically a disaster. So what did you find when you looked under that perfect 1.00 score?
We had to look at the average predicted chance of being shortlisted, and we broke it down by gender for Model A. The results. Well, they show that men were predicted to be shortlisted 56.4% of the time. Women, only 24.7%.
Wow. Okay, that is a huge disparity. Men were getting shortlisted more than twice as often. So that high accuracy score is basically just the model learning the historical bias flawlessly.
Precisely. Model A just figured out that being a man was a great predictor of success in this data set, and it leaned on that feature. Hard. But now, look at Model B, the one we restricted, the one that couldn't see gender. The moment we took away that bias feature, its raw performance dropped. Accuracy fell to 0.75. Precision went down to 0.62.
Okay, so I'm only focused on performance. That is not good. That 20% drop in accuracy looks like a failure. You're telling me I have to use a less accurate model to be fair.
And that is the absolute key moment in responsible AI. You have to stop and ask, what is the cost of that perfect accuracy? In this case, the cost was a massive ethical failure. And when we checked the probabilities for Model B, the predictions became so much more balanced. Men were shortlisted 35.9% of the time, and women 41.6%.
Wait, so Model B actually favored women, just slightly. But the main thing is they're in the same ballpark. The drop in performance actually bought us fairness. So how do we move beyond just looking at these numbers? How do we quantify that jump in fairness?
We use the tool designed for exactly this. It's a metric called the Disparate Impact Ratio, or DIR.
Okay, DIR. Let's unpack that. It sounds official. What is it actually measuring?
It's just measuring the relationship between the selection rates of two different groups. It compares the rate of a good outcome, like getting shortlisted, between what we call a protected group and an unprotected group.
And the formula is pretty simple, right? The selection rate for the protected group divided by the rate for the unprotected group.
Exactly. So if we're testing for bias against women, it's just the percentage of women selected divided by the percentage of men selected. It gives you this one simple ratio that tells you the story.
And what are the numbers we need to remember for this ratio? I know 1.0 is perfect fairness.
A ratio 1.0 means both groups are being selected at the exact same rate. That's the ideal. The general legal and regulatory rule of thumb is called the 4/5 rule. It basically says that an acceptable range of fairness is between 0.8 and 1.25. If your ratio drops below 0.8, that's a red flag for potential bias.
Okay, let's apply that back to our models. What did the DIR tell us about Model A, the one that looks so good on paper?
For Model A, the super accurate but super biased one, the DIR was a shocking 0.44. That is way, way below the 0.8 threshold. It's quantitative proof that the model was discriminating no matter what its precision score said.
A flashing red light, ethically speaking. And what about Model B, the one that took a performance hit to be more balanced?
Model B, the one that couldn't see gender, gave us a DIR of 1.16. That falls right in the middle of that acceptable 0.8 to 1.25 range. So the DIR proved it. Sacrificing a bit of raw accuracy got us to a place of ethical compliance.
Okay, so DIR helps us spot the problem. But if you're actually building these things, you realize pretty quickly that fairness itself isn't just one single idea. There are like 4 different flavors of it.
Gets the next level, yeah.
Yeah.
You have to choose which definition of fair actually matches the goal of what you're building. And in the industry, we mostly talk about 4 competing definitions.
Let's start with the one that's closest to DIR, which is demographic parity. What's its main goal?
Demographic parity has a very simple goal: equal selection rates across all groups, full stop. It's about proportional outcomes. You might use this for, say, entry-level job screening, where your main goal is just making sure your initial pool of candidates is really diverse.
Sounds great for representation. What's the downside?
The big limitation is that it completely ignores whether someone is actually qualified. It only cares about the final numbers. So a model could be making totally random, terrible decisions, but as long as the outcomes are proportional, it would pass the test.
Okay, so for a high-stakes decision like a loan or making sure a great candidate doesn't get screened out, we need something more than just equal numbers.
Exactly. For those high-stakes cases, you'd probably look at equalized odds. The goal here is way more sophisticated. We want equal accuracy for all groups. That means the model has to have an equal true positive rate and an equal false positive rate for everyone.
Let's break that down for the hiring example. A true positive is.
A true positive is when the model correctly identifies someone who is actually qualified. Equalized odds make sure that a qualified woman has the exact same chance of being correctly identified as a qualified man. The rate of getting it right has to be the same.
And a false positive, that's a bad mistake.
A false positive is a huge mistake. It's predicting someone will succeed when they won't. If you're giving out loans, that's a disaster. Equalized odds make sure the model isn't making that type of error more often for one group than another.
That makes sense. What if our only concern is making sure that deserving people don't get missed?
That brings us to the third one, equal opportunity. This basically simplifies equalized odds. It focuses only on the true positive rate. It's all about ensuring that the people who are actually qualified are treated equally. You'd use this for things like scholarships or promotions, where the main goal is just not to deny a great opportunity to someone who deserves it.
And the last one, what about for something really sensitive, like a medical diagnosis?
In that case, we often use predictive parity, which is also called calibration fairness. The goal here is to make sure the probabilities the model gives you mean the same thing for everybody. So if the model says you have an 80% chance of having a disease, that 80% has to be just as accurate for a man as it is for a woman or for any racial group.
So we have these 4 different goals, and it seems like choosing one means you can't have another, right? Like, if you aim for perfect demographic parity, you might violate equal opportunity if the groups just happen to have different qualification levels in the real world. You have to choose.
That's the hardest part of responsible AI. It starts being a pure tech problem and becomes a philosophical one. You're literally designing your ethical priorities directly into the math.
The good news, though, is that we don't have to build these models from scratch every time we find a problem. There are tools to help us fix this.
Oh yeah, the solution space is growing fast. A fantastic open source library for this is a Python tool called FairLearn. It's built to do exactly this: detect bias with metrics like DIR, and then apply fairness rules to the model while it's training.
Okay, so let's go back to our villain, Model A, with that terrible 0.44 DIR. What happens when you use FairLearn to apply a rule like demographic parity to it?
The change is immediate and dramatic. When we applied the demographic parity constraint to Model A, its DIR shot up from that awful 0.44 all the way to 0.82.
So a jump from 0.44 to 0.82. What does that actually mean for the people applying for the job?
It means the model went from shortlisting women less than half as often as men to shortlisting them at a rate that is now within that acceptable 4/5 rule range. The model is now accountable.
But let's be real about the trade-off. We did have to take a performance hit earlier to get that fairness. This is the fairness-accuracy trade-off. If I'm an engineer and my bonus is tied to performance, why would I accept any drop in accuracy?
Because the real goal of a good AI system isn't just the highest number. It's building something that is ethical, inclusive, and trustworthy for everyone it serves. If your perfect accuracy is achieved by harming half your users, then that accuracy isn't just fragile, it's unsustainable.
I think the car analogy you mentioned is perfect. You're tuning an engine.
Exactly. You might give up a tiny bit of top speed, that raw accuracy in exchange for safety features and reliability. You want a car that works well for every single person who gets behind the wheel, not just the one test driver it was built for. Trust is the real prize here.
And for anyone who wants to go deeper, FairLearn is just one tool in a whole ecosystem right now.
For sure. If you really want to get into deep analysis, there's AIF 360 from IBM, which has over 70 different fairness metrics and tons of mitigation algorithms you can try.
And for transparency, for understanding why a model made a decision, there are tools like Ashape and Lime.
Right. Shape is great for explaining individual predictions, and Lime helps you see how small changes in the input can change the output. And if you're a visual person, Google's What If tool is fantastic for interactively exploring bias in your data. All these tools are part of a movement toward accountability by design.
So the big lesson today is that the most dangerous AI isn't the one that's obviously broken. It's the one like our Model A with its perfect 1.00 score that looks flawless on paper but is hiding a huge ethical failure. Relying only on those classic performance metrics is it's not enough. You need dedicated tools like the disparate impact ratio to find the truth.
That really is the heart of responsible AI. Bias isn't always intentional, but fairness absolutely has to be. It forces us to move beyond just chasing high scores and to start actively designing our human values, our character, into these systems.
Because the goal is to make sure the intelligence we build serves everyone, not just the people who are well represented in the old data. When we automate decisions, we are automating ethics.
And that leaves you, the listener, with a final, really difficult question to think about. If you were the one in charge of a high-stakes system, maybe for loan approvals, and you knew you couldn't make it perfectly fair by every definition, which ethical goal would you prioritize? Would you choose demographic parity to make sure selection rates are equal? Or would you choose equalized odds to make sure accuracy is equal and you're preventing harmful mistakes? Your answer to that question says a lot about your core values.